Hey y'all, today we're going to go ahead and look at polyprotic acid titration curves. Polyprotic acids are acids which have more than one acidic hydrogen. Now, many acids have more than one hydrogen. However, not all acids have more than one acidic hydrogen. We're going to focus on those today. And we're going to look at what their titration curves look like, and also briefly how to analyze the different elements of those polyprotic titration curves. Let's get started. One thing to be aware of with polyprotic acids is that each of the acidic hydrogens is different. So let's take, for example, the polyprotic acid, phosphoric acid, H3PO4. Now, phosphoric acid is actually a triprotic acid. That means there are 3 acidic hydrogens associated with this acid. It's a weak acid, but it's one of the stronger weak acids that we have. As a result, when we look at how phosphoric acid dissociates, that first hydrogen that comes off is actually pretty easy to pop off. It's not quite strong, but it's pretty close. Then we have a second hydrogen that pops off. Now, the thing to note about that second hydrogen that comes off is it's actually coming off of the conjugate base of the first hydrogen that has popped off. So when the first hydrogen pops off of H3PO4, it creates H2PO4-. Then in the second acidic hydrogen, what we see is that second hydrogen popping off of the H2PO4- to create HPO4-2-. And then there's the third acidic hydrogen popping off, which creates PO4-3-. So what we have here are some situations where the conjugate bases of one step are actually the acids of the next step. And that's what's happening in these polyprotic acids. It's important to note that each of the acidic hydrogens of a polyprotic acid will ionize or pop off depending on its relative strength, which means its Ka value. So if we remember, the larger the Ka values are, the stronger the acid is. So the first hydrogen that pops off is going to have the greatest Ka value. It will be the strongest of the acids. The second hydrogen that pops off will have the next highest Ka value, and the final hydrogen that pops off will have the lowest Ka value. And they do this in order. In general, we're only going to look at calculations, like mathematical calculations, with the first of those Ka values. However, we might be asked to interpret titration curves with the others. So let's take a look at what that would be. Whenever we look at a titration curve, we need to analyze a couple of things. We need to analyze, first of all, whether we're looking at an acid or a base that's being titrated with an acid or a base. We need to know if it's a strong or a weak acid or base that's being titrated. And finally, we can now look to see how many acidic hydrogens there are within that acid. So let's take a look at this curve for a moment. This is a representative curve of a polyprotic acid. The way I know it's a polyprotic acid is because it doesn't just have one equivalence point, it actually has several. And as a result of having several equivalence points, we know that each of those equivalence points would be representative of the subsequent polyprotic acid's next conjugate. One thing you might need to do on one of these curves would be to identify where those equivalence points are for each of the acidic hydrogens. The other thing that you might need to be able to do is identify the Ka values for each of those acidic hydrogens. So let's talk about how you would do that. So again, the 2 points that you want to be able to look for on these polyprotic curves are the equivalence points for each acidic hydrogen, but also we're going to be able to use those halfway to equivalence points to help us determine the Ka values for each of the acidic hydrogens. One thing to remember is that the pH of your halfway to equivalence point is, in fact, the pKa of that hydrogen, of that acid, which means that the Ka value could be calculated. So here's the polyprotic acid, phosphoric acid again. When we look at the titration curve, I've populated it with all of these different numbers and equations. So let's go step by step to figure out what's going on. The first neutralization that's going to happen is of the first acidic hydrogen, that third hydrogen. This is where H3PO4 is going to be neutralized into H2PO4 minus. When that happens, at halfway to equivalence point, the concentration of H3PO4 and H2PO4 minus are going to be essentially equal. This is our first halfway to equivalence point. That means the pH of that point, 2.12, is equal to the pKa of my first acidic hydrogen. Now, beyond that, you're not really going to have to use these calculations, but you will need to analyze for how many acidic hydrogens there are. So if we look at this curve beyond that first equivalence point, we're going to see that we have 3 separate equivalence points. There's an equivalence point at 4.67, the equivalence point at 9.46, and finally the third equivalence point at 11.93. These represent the 3 acidic hydrogens. And you'll notice that the pHs get higher and higher each time. And also the halfway to each of those equivalence points gets higher each time. This is representative of each of those successive acids becoming weaker and weaker as you go along the titration curve. The other important thing to note is that at each halfway to equivalence point, we still have equal amounts of the acid present and the conjugate base that's being created. The other thing to keep in mind in this titration curve is that even though each of the successive acids gets weaker and weaker, it actually takes the same number of milliliters of base to neutralize each one. So to reach your first equivalence point took 50 milliliters of added base. To reach your second equivalence point, it took 100 milliliters of added base, so 50 more than the first. And to reach the third equivalence point, it took 150 milliliters of base, so 50 more than the second. This is important to remember because neutralizations behave the same way whether you're neutralizing a strong acid or a weak acid. And in polyprotic acids, you neutralize each acidic hydrogen independently. The final thing you might be asked when looking at a polyprotic acid's titration curve is what is the dominant species? The dominant species of any polyprotic acid is going to be the species which obviously remains at highest concentration in the solution. When you look for the dominant species, you have to think about where you are on the curve. If we're at our first equivalence point, we have equal amounts of our first acid, H3PO4, and its conjugate base, H2PO4 minus. So before that equivalence point, we have more H3PO4. After that equivalence point, H2PO4 minus becomes dominant and remains dominant until that second halfway to equivalence point. So when your second equivalence point, or you're halfway to that second equivalence point, what you need to think of is that half of that first conjugate base, which is now your acid, H2PO4 minus, has reacted away. It's formed its own conjugate base, HPO4 2 minus. So at the second halfway to equivalence point, what we're seeing is that all of a sudden the HPO4 2 minus becomes dominant, and then it stays dominant until the third halfway to equivalence point, at which point the PO4 3 minus becomes the dominant species. So when we're thinking about dominant species, we have to think about where we are on the curve, what has reacted away, and what remains. So that wraps up today's video. Let's do a quick recap. Today, we spent the time talking about polyprotic acids and being able to analyze their titration curves, and in doing so, identify the Ka values for each of the acidic hydrogens. Also, we learned how to analyze a titration curve and a polyprotic titration for dominant species present. This video was written, directed, filmed, and edited by Elias Mukdisi and James Zhang. Thank you all for watching it. I hope you enjoyed it, and I'll see you in the next one.